Okay, so here's how we would conduct an analysis of variance using RStudio. What I'm going to be doing is analyzing the yield data according to three different types of fertilizer, and this data were provided and analyzed by Graffen and Hales. So the first thing we would do is import our data, and I've imported it already. It's fertilizer comma delimited file, and here is the data, how it looks in terms of the overall structure. You'll see that we have 10 observations of the yield with one type of fertilizer, 10 with the second, and 10 with the third. Now, the first thing we should be thinking about in an analysis of variance is plotting our graphs and relationships. So this is what we're going to be doing using strip chart. Now, strip chart is a way of depicting the data, but for closely overlapping data, what we have is a slight jitter introduced, and here I have a jitter of 0.04. So here what we have is the data all laid out with fertilizer type 1, 2 or 3, and there we have the yield in tons, and it's all done with this simple command, strip chart. So it appears that the yield is slightly higher on average in fertilizer 1, but can we be confident of this? What we would then next do is fit a analysis of variance model, a general linear model to the data. So this is what we're going to do now. We'll call the result of that fit analysis, and that analysis is an object with many different properties, but you'll see that what we have here is yield is related to fertilizer, and you'll notice importantly that I have used as factor. We can simply use factor if you like for fertilizer, because if not, with this linear model it would treat fertilizer as a continuous value, since we have used 1, 2 and 3 rather than A, B and C in this case. So we've got yield, we've got the fertilizer, and here we've got where the data actually comes from. It's from fertilizer CSV. So we've now fitted our linear model, but what we would like to do is to understand the structure of that fitted model. So here what we do is we call up the ANOVA for that analysis. And what you'll see here is the partitioning in terms of sums of squares and degrees of freedom that you were introduced to in the theory. Two estimates of the population variance, one judged from the variability between the fertilizers and the other generated by an estimate of the variability within the fertilizers. These two happen to be highly significantly different according to the F distribution, in that the probability of us getting that test statistic of 5.7 or a more extreme, if the null hypothesis was true, is really very, very small. So we reject the null hypothesis that the population means are all equal. Now, before we can really confirm that interpretation, what we really need to do is to look at the plots to see whether in fact our assumptions underlying the fit of the analysis of variance model are indeed valid. So let's have a look first of all at the plot of the residuals, and here what I'm saying is plot, and this object of analysis has many different features, including an ability to plot the residuals, and that's the very first plot. So I'm saying which equals 1, and here you'll see the residuals versus the fitted values. These are the predicted values of yield for each of these different cases, and what we can see here is that the overall variance is relatively homogeneous for all levels of those fitted values. Now, that's one assumption. The other assumption, of course, is that we have normality in terms of the overall distribution of residuals. And here we can use a QQ plot to evaluate this particular assumption, or actually look at the distribution of the residuals themselves. For a QQ plot, which is a quantile-quantile plot, if indeed we have a normal distribution, if we follow the normal QQ plot, then it would follow a straight line. Here we have something of a cause to be worried about, because quite clearly there is a bit of a skew in our data, in that we have a little bit of a tail up here where it's not sticking overall to that straight line. So let's visualize that more directly, and we can first of all define the residuals, the standardized residuals off that model fitting, simply calling up a variable name sresids, and R standard is the function for extracting those residuals. And then we're going to simply plot the histogram of those residuals, and this is what we see here. So although we don't really have that much data to really evaluate this assumption of normality, there does seem to be something of a positive or right-hand skew in these data, but nothing too much to get concerned about. So up above, we have found that there's a significant effect of fertilizer, i.e. that the probability of us getting that test statistic, or a more extreme if the null hypothesis is true, is really very small. So we're going to reject the null hypothesis. So the fertilizers do seem to give different yields, but wherein lies the difference? Perhaps just one of the yields, according to one of the fertilizers, is different from all the rest, or maybe they're all different. We can address this question by doing so-called post hoc tests, and the post hoc test that I'll be calling up is the two-key honestly significant difference test. Here it is, two-key HSD, and what we're going to be doing is calling up AOV analysis. That's the analysis of variance, another form of doing an analysis of variance on that overall analysis, and this is what we find with the two-key HSD test. What we can see here is that the big difference lies between 2 and 1, and yet we can't really reject the null hypothesis that there is no difference between 3 and 1 and 3 and 2. So 2 and 1 are really the ones that differ from one another, and we can see this if we go back to our original plot here, with 2 and 1 contributing most to that overall difference between fertilizers, rather than 2 or 3. Thank you for listening to this R Labs tutorial video. If you found this useful, you might be interested in our free online Moodle course, or check out and subscribe to our YouTube channel.